Chris, and I'm doing research based on this course, and so I have some questionnaires to pass out. You don't need to put your name on it. You're not being graded on it, but this feedback would be nice to have. So if it would be possible for you guys to fill it out for me. The people that have worked with me already, there's like one of the first questions, you can just say that you worked with me instead of answering it all. Thanks.
I'm Stephen Bird.
I'm Haitian.
I'm Zizan, and the project we designed was called Armstrong Shuttle. So, as many of you know, Purdue is famous for the number of astronauts that we produce, especially the most famous astronaut, Neil Armstrong.
Could you sit down? Thank you.
All for that, and somewhat of a replica of lunar lander from Armstrong's mission. So we wanted to do this for a couple of reasons. First, because of the history of Purdue behind it. Also, it's more of a children's toy. It's easy to use. It just has moving parts. It's not encountering or anything. It can inspire children, potentially, especially children who love space and exploration. And it can be for anyone, any child can use it. So we wanted to market this for children 5 to 10 years old. Like I said, it's not a game. It's nothing complicated. Just moving toys. So that's why we chose that age range. And it doesn't matter who the child is. It can be for anyone that is interested in that kind of stuff.
Okay, then I will talk about the structure of the toy. And the toy, our toy is made up of 4 main parts. The first one is the main body. It's like the cabin of the shuttle. And then is this one, the Jason linkage is used to achieve the working motion. And then we use gear set in the middle of the toy to simulate the motion of astronauts going out of the cabin. And the motor is used to power the linkage. So, and the gear set can be operated manually. And the 2 main motions of our toy. The first one is the Jason mechanic. And you can see in the picture. There are 2. This is the simulation of the Jason linkage. As you can see in the picture, there are 2 data points here. They are remain to be relatively static in the whole motion. So if we pin these 2 points to the cabin, then we can achieve the best performance. And the next motion is the gear set. It can drive the door open while to pull out the platform at the same time. Go back to the. If we open this door, and the motion will transfer by the gear set to make this platform out at the same time. And we design the motion here to make the steel up straight while the platform will go out at the same time. Okay. Then I will talk about the manufacturing and assembly.
Okay, thanks. I'm going to say something about manufacturing and show you our virtual model. We 3D printed the main body of our model, the top and bottom parts, and the door, and the platform in it. You can see the door with the steer and the gear, right? And after we got the 3D printed part, we glued the top and bottom parts together, and we printed the model. We painted the model. Another technique we use is laser cutting. We laser cut almost all the thin boards to compose the Theo-Jensen mechanism, and we cut some boards to support the motor and to cover the main body. Also, we cut some gear-shaped boards, and we we glued 4 of them together to make a gear. This is the virtual model, some views of our virtual model. And you can see the overall view via this picture. After this door open, as Zhishang says, the platform will come out and there will be a fitting on it. And the astronaut can go downstairs and land the moon. And this is the mechanism. Actually, we didn't mention the motor was set reversed before we submitted it, but the video is just to show you that it works. And I'll pass to Zhešen to show you the real model.
Okay, the circuit part is we use the motor is with the resolution is 1,800 revolution per minute, and the gear ratio is 200, so we can reduce the speed from very high speed to low speed for our motion. The motion is like 1 second per revolution now, and the battery we use is 1.5 voltage, and we have 2 motors here connected parallel to make sure the power is enough for, like, each motor is control one side of the motion to make sure we have enough power to drive it. And we have a switch here to control the whole motion. We just open it, we can run it. And this is the after assembly. Yeah. And we have a video when we run it. That's motion, we correct the motion. That's counterclockwise for the motion. And the door is open, the platform is goes inside. Yeah, that's all. So I'm going to do the other first. Okay.
Okay,
Yeah, it's really like this. And I'm not sure it works here. The table is like too smooth. In our, that's the place we want to improve. We put some plastic and the feet to increase the fraction to make sure you can work on the table, right? And now we done for that one. This is the door, and we open it, and like this down here is you can see the gear, transmission, and if we open it, you see the platform comes out, right? And then we turn it. Yeah, you'll get it back. And one more thing is, the original design is actually 0.1, I mean for the theodresen, the motion part, the thickness should be like 0.15, but actually we cannot find the thickness of the plastic on the market. So we reduce the thickness of that. So it makes our body is like a little bit flexible. Yeah. So and that's the place we can improve in the future. And you will run now. Yeah, but here is like the fraction.
Yeah.
So that's the way we need to improve.
So question.
Yeah, question.
This is a 4-legged system.
Yeah.
I don't know if you have background of gate mechanisms for legged systems, but usually from the point of view of the support polygon stability, 6-legged systems are much stable. You can have 3 legs on the ground at the same time,
Yeah.
which is a problem with these kinds of systems. Because you will have 2 legs if you're doing a drawing.
It was like looks balance.
Right. So what was your rationale for
We don't want to use the
maybe design has the restriction of the dimension. So if we use 3 legs, it will be 2.
Any other questions?
It's a very minor part. You guys have designed
Now we know we have to make sure that the feet is always perpendicular with the ground, right? So now we are using like the gravity stuff, like use these weights to make sure it's always perpendicular to the ground, but it doesn't work pretty well.
Yes.
Because it is
Yeah.
So what could you possibly do to improve that?
maybe we can use metal material.
Okay.
That would increase the weight.
Yeah.
Motors carry.
Or handsome, like tiny things.
So you can
But we can also. But we want mainly to feel because we want to increase the contact area.
Right, but if you're looking at a line contact between the foot and the surface,
It's not stable.
so you can actually use some kind of traction curve which is static, which doesn't have